Hello everyone, my name is Manuel Brenner, and today I will tell you how to integrate multimodal data for the joint generative modeling of complex dynamics. Our paper is located in the field of dynamical systems reconstruction, where a dynamical system is a function that determines the time evolution of a state within a state space, and these can be represented via ODEs or recursive maps. In dynamical systems reconstruction, the aim is to reconstruct such an underlying, usually unknown dynamical system from measurements that constitute the training data. There are many different dynamical systems reconstruction model architectures in the literature, so they can be represented by recurrent neural networks, neural ODEs, reservoir computing, but also other techniques. And then the aim is to find a training algorithm to train this DSR model in such a way that it constitutes a surrogate dynamical system representation of this underlying dynamical system, such that the long-term dynamics agree with the ground truth system in terms of geometric agreement, temporal agreement, and the overall topology of the dynamical system. There are several challenges of dynamical systems reconstruction from empirical data, namely that empirical systems are often observed via different modalities, via multiple channels at the same time potentially. They can also be non-Gaussian discrete, so ordinal ratings in psychology, event counts like in climate science, where you have discrete events, temperature curves and wind directions measured simultaneously, and you also often have missing data and or partial observations. Then the idea is that this underlying system is measured via some kind of measurement process, which can be quite complicated, and then the dynamical systems reconstruction model is in turn coupled to these observations and explains them via so-called observation models that take these distinct distributional assumptions and statistical models into account. Another challenge for DSR from empirical systems and for chaotic dynamical systems in general is that chaotic dynamics lead to exploding gradients because the Jacobians, the product of Jacobians that occurs when computing the maximum Lyapunov exponent of an RNN also occurs in the training loss with backpropagation through time-based training methods. And previous work in our group actually showed that this is bound to happen for all chaotic dynamics. So this is in principle unavoidable no matter what kind of architecture you use and what kind of RNN model you use, because precisely this RNN constitutes a surrogate model of this chaotic dynamical system, so it itself has to constitute a chaotic dynamical system. The good news is that this gradient explosion can be remedied by so-called teacher forcing techniques, where the idea is that we, during training, freely evolve RNN states, but we pull them back in a specific way onto data-inferred control states. And that allows us to both capture long-term dynamics, but also to avoid these exploding gradients. And the idea of teacher forcing is to do this only weakly, either sparsely in time, or weakly by building this linear combination of data-inferred control states and freely evolved states in a way. Again, we don't want to overforce the system, so we don't want to basically tell it what it has to do, but we want to push the burden on the free evolution of the RNN states during training, but pull it back enough so the gradients are not exploding. And we explored this in depth in two recent publications at the last two ICML conferences, where we achieved state-of-the-art performance across many dynamical systems reconstruction tasks, including many challenging real-world systems. And the aim of this work was to really extend this to multimodal data, to non-Gaussian data. Because one of the challenges of teacher forcing techniques is that they require the inversion of the observation model, because we want to have this teacher forcing signal. We want to know how to pull trajectories of the RNN back on track, but this is only straightforward for the Gaussian case because the latent process is Gaussian. And if the observations are also Gaussian, there's a nice relationship that can be inferred quite easily. But for multimodal data or non-Gaussian data, this is not as easy anymore. So we leverage the power of this encoder-decoder framework of multimodal variational autoencoders, which have been very successfully applied to multimodal data in many domains. So our approach is called multimodal teacher forcing, and as I already mentioned, it uses this multimodal variational autoencoder framework to first construct a latent representation across multiple modalities or non-Gaussian data, and this can be very flexibly parameterized, for example, via temporal CNN, RNN transformers. We tried a lot of these within our paper, and then to use this latent representation to provide a teacher forcing signal in the latent space of the DSR model that we are training. And this can again be parameterized by many different architectures. We tried several in this paper, for example, a specific dendritic PLRN, but also LSTMs, GRUs, classic RNNs. And then again, to sum this up, we encode this multimodal data via the approximate posterior and then use this as a teacher forcing signal of the DSR model, and then couple both of these latent codes via shared decoder models to reconstruct the observations. So how does this look like in terms of the loss? So the first idea in the framework of multimodal variational autoencoders is to use the DSR model as the MV prior. So we call this a consistency loss because this basically means we have two latent codes of the DSR model and of the encoder of the MV, and we want them to agree as closely as possible because we say this is the prior of the latent states. Then, as a second step, we couple the DSR model to the same MV decoder models because, again, this further ensures this consistency between the two latent codes. And these decoder models actually share their parameters. And this, in turn, leads to this combined MTF loss, where we basically identify this consistency loss, we integrate this DSR loss into the classical MVR loss. And what we saw in ablation studies is that all of these loss terms actually contribute meaningfully to improve reconstructions within this framework. One nice additional component of why this works so well on all kinds of data is that optimal forcing in the context of teacher forcing techniques leads to these smooth and easy to navigate loss landscapes. So with different data sets and different settings, we actually observe this nice property of the loss landscape to look quite well navigable and smooth in the context of optimal teacher forcing strengths. A couple of things we can do with MTF. MTF enables DSR in challenging settings, for example, for highly noisy data, where using multimodal data integration, we can even reconstruct the Lorentz attractor approximately for extremely noisy Gaussian observations. We can do cross-modal inference, where we have, for example, missings in one of the modalities, and even for partial observations, where, for example, we only observe the X component of the Lorentz attractor. We found that the encoder model of the MTF actually automatically learns these delay embeddings, so it unfolds the attractor in state space. We can, for example, also use this exclusively on categorical variables. So this result actually quite surprised us because we used this one-hot encoding, this categorical representation of the Lorentz, where only one of the bins is active, which encodes the bin in which the state is currently is in. So via this one-hot encoding. And then we trained on this basically 64 symbols, these 64 bins. And the only information we gave the MTF is again this representation. And then purely with that, we could approximately reconstruct the geometry of the true Lorentz attractor. And what is also notable is that the maximum Lyapunov exponent basically almost perfectly agrees across different runs, which was very close to the ground truth value of 0.9. This means that this framework even allows dynamical systems reconstruction purely from these categorical variables, which you can imagine leads to a lot of interesting applications, for example, purely to spike process, psychological survey data, language data, and many others. We can also do multimodal dynamical systems reconstruction, for example, from human fMRI scans. So this is a type of neuroimaging technique, functional magnetic resonance imaging. And in this case, we combined this imaging data with categorical observations, which basically encoded the cognitive tasks that subjects were performing in the scanner. And this multimodal data integration led to improved reconstructions of the imaging data and structured the latent space according to these cognitive tasks. And as a second application, we combined hippocampal spike counts, which were like count processes, with behavior, in this case, a rat moving on a platform. And then we integrated these count observations and the Gaussian observations, and basically led to computed the couple of spike statistics and predicted basically the behavior and the spikes on the test set, on an unobserved test set. And what we found is that, again, in this case, multimodal data integration really improves spike statistics. So having the location data on top of the neural spikes leads to overall across a range of spike statistics, better reconstructions. And we again find this joint latent space which encodes both the position of the red and the spiking of the neurons. So we benchmarked this against a lot of different other approaches and found that MTF really outperforms all other techniques by sometimes quite large margins on experimental data sets and on a number of benchmark systems, and even enables DSR in settings that are impossible with all other tested approaches. We have a code base up online, which includes several Jupyter notebooks with tutorials on how to actually train these models and how to evaluate them. So in summary, MTF provides a really flexible framework which you can apply to perform DSR from multimodal but also discrete observations. It even enables DSR from purely categorical observations, which opens up a number of interesting applications. But it also enables multimodal data integration and DSR on several challenging experimental data sets. Thank you for your attention.